Okay, you are most welcome once again to my YouTube channel. It is still your tutor Peter Ikaja, and now I am bringing out something very exciting, an alternative of what we have been doing in integration by parts, but for specific integrals, where you can actually go through another route and get the same answer as we did in integration by parts. That's why I'm calling it the basic technique of integration by parts. It can be a simple technique, it can make his life a little bit easy, and I will clarify more as we try out this example. Now, what we only do here is we draw a simple table whereby we have a column for differentiation and then a column for integration. Now the question comes, which function do we differentiate and which function do we integrate? We differentiate a function that can be differentiated a number of times until we reach out a zero, until the derivative becomes zero. We shall put that function under differentiation. And when you look at x sine x, the best function that can be differentiated until we get a zero will definitely be x itself. And that means sine x has no option other than being under integration. Now, should you differentiate x with respect to x, you definitely get 1. Then you have to integrate sine x. When you integrate sine x, you get negative cos of x. Do the same again, differentiate 1 with respect to x, you get a 0. That's our target. And then when you integrate negative cos x, you will get negative sine of x. So what you're now going to do is we're going to simply draw these arrows in this format. So I have an arrow in that format and then this arrow in this format. We leave out this, and then we leave out that. You must observe that pattern very well. Now, we can easily just write the result. We can say our integral of x sine x dx is going to be equals to. Now, you're going to use this pattern. As you get x and multiply it by negative cos of x, the pattern is the result you get, you must multiply it by a positive. And the next one, you must multiply it by a negative. So it's positive, negative, positive, negative, positive, negative. That's how the pattern continues. So it means we're going to say x sine x, integral of x sine x dx is equals to x times negative cos of x. That means I'll have negative x cos of x. And then you multiply it by a positive. Of course, when you multiply it by a positive 1, nothing changes. But then when you come here, it's 1 times negative sine x, which is negative sine x, but there's this negative here. So it makes it a positive sine x. And do you know what? We are done with this integral. As simple as that. Let's look at number 2. Okay, so number 2 says find integral of x squared cos of x with respect to x. Should you recall this very well? If we used the other formula for integration by parts, we're supposed to do it twice for us to have the result for this question. But here it will be as easy as realizing that it's x squared that we can differentiate a number of times until we come up with a 0. So x squared goes under differentiation, cos of x goes under integration. When you differentiate x squared, you get 2x. When you integrate cos of x, you get positive sine of x. When you differentiate 2x, you get 2. When you integrate sine x, you get negative cos x. When you differentiate 2, you get 0. That's when you differentiate with respect to x. And then when you integrate negative cos of x, you will get negative sine of x. Like we said, should you have a 0 here, you've achieved the target. So we draw these diagonals. So I have that. We have that. We have this. And that means our answer is going to be integral of x squared cos of x dx is going to be equals to, remember the pattern, plus negative, and so on. So it's going to be x squared multiplied by sine x squared multiplied by sine x, Now it is 2x times negative cos of x, but then you multiply by a negative, that will be plus 2x cos of x. And then you have 2 times negative sine x multiplied by a positive, you will get a minus 2 sine of x plus a constant. And that is our answer. Very interesting. Let's look at number 3. So they're telling us to find integral of x cubed sine x with respect to x. Again, we can clearly see that it is x cubed that can be differentiated a number of times until we come up with a 0. So it goes under differentiation, that is x cubed, then sine x goes under integration. When you differentiate x cubed, you get 3x squared. When you integrate sine x, you get negative cos of x. When you differentiate 3x squared, you get 6x. When you integrate negative cos of x, you get negative sine of x. When you differentiate 6x, you get 6. And when you integrate negative sine x, you're going to get positive cos of x this time. When you differentiate 6, you get a 0. And then when you integrate cos of x, you get positive sine of x. Then we have the diagonals. We have that go with that, this go with this, 6x go with this, and then 6 go with that. We have achieved a 0, that's why we stopped. And then we follow the pattern, positive, negative, positive, negative. You know, when you look at this integral, if we had to use the formula for by parts, we would go through the process of by parts 3 times. So this makes it a little bit easy and less tedious for us. So I can conclude that integral of x cubed sine x dx is actually equals to x cubed with a negative, because we are having cos of x being a negative. Then we have, first get negative 3x squared. Sorry, get 3x squared multiplied by negative sine x. But then there's a negative we have here. There's a negative we have there. So at the end of the day, we have positive 3x squared sine of x. And then we have 6x, it is of course a positive here, so we multiply by that, it means we shall have 6x cos of x. And then we have minus 6, because there is a minus here, that's why I'm saying minus 6, multiplied by sine x, it will be minus 6 sine x, and then plus a what? Plus a constant of integration. That is our number 3. Finally, let's look at number 4, and then I will give you some simple questions again to try out. So when you look at this, they're telling us to find integral of x exponential x with respect to x. The basic technique can as well work here. So we shall simply say we are going to differentiate and then integrate. What are we going to differentiate? That's what we need to ask ourselves. What are we going to differentiate and what are we going to integrate? Definitely, it's only x that can be differentiated a number of times until we get a 0. So I'll have x there. Then exponential of x will be there under integration. Differentiate x, you get 1. Integrate exponential x, you get exponential x. Differentiate 1 with respect to x, you get 0. Integrate exponential x with respect to x, you get exponential x. So we have our diagonals drawn in this format, and then that. So positive, negative. So we go on and then write the product, the result. So integral of x exponential x with respect to x is actually going to be as simple as x exponential x and then minus exponential x plus a constant of integration. Finally, example 5, and that will be the end of our examples. Then I give the exercise. Okay, there we are. We are now having x squared exponential x dx. If we are to use the formula by parts, we're supposed to go through it 2 times to get this integral. But here, shall have x squared under differentiation, shall have exponential x under integration. When you differentiate x squared, you get 2x. When you integrate exponential x, you get exponential x. Differentiate 2x, you get 2. integrate exponential x, you get the same exponential x. Differentiate 2, you get a 0, which is our target for stopping. And then integrate this, you get the same exponential x. So from here, we now have our diagonals drawn systematically. So that at the end of the day, this is plus, this is negative, this is plus. So at the end of the day, we shall say integral of x squared exponential x with respect to x is equals to x squared uh, exponential x. It's now going to be minus 2x exponential x, and then plus 2 exponential x plus a constant of integration. And we're done. So this brings us the end of the examples. I'm now going to give you a few examples, a few questions to try out so that you can perfect. Please don't forget to subscribe before you leave this channel, because it's only when you subscribe and turn on the notification button that we always update you whenever I upload new content. Okay, this is our simple exercise, and I think after this you will really find yourself very, very good at doing these questions that involve integration by parts, though you take a shortcut and make life easy than going for the use of the formula more than one time. See you in our next tutorial as I bring for you something else as the continuation of our topic, integration. Bye-bye.